Gravity, or gravitation, is one of the four fundamental forces. Gravity is readily associated with mechanics, because one of the most important applications of mechanics is that of planetary motion. And planetary motion is ruled by gravity. This is the side of the Moon that we can see from Earth. Right here is the Sea of Tranquility, which has a special place in the history of human civilization. It was here, on the 20th July 1969, that the Eagle landing module of Apollo 11 landed, and Neil Armstrong and Buzz Aldrin were the first humans to put their foot on the Moon. The two astronauts spent 21 hours on the lunar surface. They left behind a reflector, a seismometer, and they took with them 22 kilograms of moon rock. The moon landings relate to Canberra. The missions were tracked by tracking stations around the world, including the one at Honeysuckle Creek in Amachi National Park. They'd also relate the first TV pictures of Neil Armstrong's moonwalk. Moon rock has been studied in Australia, and a large piece is on display at the Titminvilla tracking station. Using the mirror left behind by Apollo 11, laser ranging stations, such as the one located on Mount Stromlo, can determine the actual distance to the Moon. The Moon exhibitions provide many examples that relate to introductory physics. For example, it is wave physics that permits the use of the seismometer that was left behind on the Moon to investigate its internal structure. Following the return to the command module, the Lunar Module, at a mass of 5 tons, was crashed into the Moon's surface at 17 kilometers per second to induce seismic waves that were then detected by the seismometer and revealed information on the internal structure of the Moon. Another example is laser ranging with the lunar reflector, which takes advantage of the kinematic equation S equals Vt. Satellite laser ranging, SLR, or for that matter MLR, moon laser ranging, is illustrated here. It involves firing a very short laser pulse to reflect off a corner cube prism on the satellite or on the Moon, and then measuring the round-trip time of flight to calculate the distance via S equals Vt. It is possible to accurately measure the time of flight to within 30 picoseconds. Since the speed of light is constant, measuring this round-trip time is equivalent to measuring the round-trip distance. And the observatory can achieve a sub-centimeter accuracy. For the Moon, these measurements have told us that the distance Moon-Earth at the closest separation is equal to 356,400 kilometers, and at the largest separation between Earth and Moon, the distance is 406,700 kilometers. We've also found out that the distance between Moon and Earth increases about 4 centimeters per year. Thus, approximately, the Moon is at a distance of 400,000 kilometers from Earth. It is also well known that the Moon's radius is 1,700 kilometers, and its gravitational effects indicate that it has a mass of 7 times 10 to the 22 kilograms, which is 1% of the mass of Earth. The Moon has no atmosphere, nor plate tectonics, and it has a different composition than Earth, which is apparent from this comparison here in this diagram. You can see that several elements are quite differently represented on Moon as compared to Earth. If you take titanium, there's a lot of titanium in the lunar lowlands and very little on Earth. Another example is the element iron, which has a concentration of more than 10% in the lunar lowlands, but is much less represented on Earth. In contrast, silicon is very abundant on Earth, but not so common on the Moon. The abundance of the elements on the Moon is the result of its origin. The origin of the Moon has long been disputed. However, it is currently understood that the Moon was created in a collision between a planetoid, Theia, and Earth, which explains its somewhat similar but then different abundance of elements when compared to Earth. Another strong piece of evidence is the alignment of angular momentum of Earth and Moon, which is illustrated here. You might wonder why I dwell so much on the Moon. I'm doing this because I think it's the perfect example that illustrates the topic of gravitation. Not only does the Moon's gravitation have effects on Earth, like the tides, and one has to overcome the Moon's gravitation to take off again when landing there as an astronaut, but also the Moon led to the discovery of the Universal Law of Gravitation, as you'll see later in this presentation. Let us look at the gravitational effects of the Moon in more detail. What you see here is the Lunar Module, which has a total mass of 15,000 kilograms. It's divided in a descent stage, which was left behind on the Moon, and an ascent stage, which allowed the astronauts to return. The Lunar Module could not be landed on Earth because its propulsion system develops at full throttle a force of 44,400 Newton. However, on Earth, the weight of the Lunar Module is 150,000 Newton, so trying to land it on Earth would result in a crash. However, the much reduced gravitational attraction of Moon allowed it to be landed safely on the Moon. This slide illustrates how the thrust was applied over time in order to guarantee a safe landing of the module on the surface of the Moon. From the diagram you see that at a height of 668 feet, the decelerating thrust was 4,000 pounds. The unusual unit and non-SI system unit pounds force, 4,000 pounds force, can be calculated to represent 18,000 Newton. So at 668 feet, 18,000 Newton had to be applied to decelerate the landing module sufficiently so that gravitation could be overcome and it could be landed safely. In general, before any landing and also for relaunch, this condition has to apply. The force due to thrust has to be at least equal to the gravitational attraction of the Moon. Let us ask the questions how the thrust force was controlled and what is actually the gravitational force. The short answers to this are rocket physics and the gravitational force is given by the Universal Law of Gravitation. The thrust force arises from the principle of momentum conservation, which applies to any system without external force. And that is the situation for a rocket. Let's look at a fixed reference system. Then with respect to that reference system, the center of mass of the rocket moves forward. And the initial momentum of the rocket is equal to the total mass, the initial mass of the rocket, times its velocity. If we now induce a negative mass change, dm, by chucking out material, exhaust gases in this case, out of the back of the rocket, then in order to conserve momentum, because we're reducing mass, we have to increase velocity. So the original velocity has now an additional contribution dV that's added to it. This means the rocket is now traveling faster. However, we now also have to consider the mass of the exhaust gases, which travel with a speed of u, typically in the same direction as the rocket. This may be surprising, however, we have to consider that we're not considering the rocket at rest, but in motion. Formally, we can now write in a third step that the final momentum is the sum of the momentum associated with the exhaust gases and the momentum at this time, a short moment later after the initial consideration, of the rocket. And we note this equation as double star. If we now combine double star equation with the one star equation on the previous page and apply thereby momentum conservation, whereby we ignore the vectors since our consideration is one-dimensional, we can rearrange equation 3, or double star, like this. The initial mass of the rocket times the initial velocity is equal to the negative mass change times the speed of the exhaust gases plus the final momentum, which is the final mass of the rocket, which is less than initially, and the somewhat larger speed. The derivation is helped if we introduce a relative velocity between the exhaust gases and the rocket, which is the difference between the final speed of the rocket and the speed of the exhaust gases. Now, substituting that in this equation, we obtain equation number 6, which we can rearrange to give us this result. After some algebra in step 7, which I don't want to go through here in detail, we arrive at this equation here. The negative mass times the velocity change is equal to the positive mass change times the relative velocity between exhaust gases and rocket. If we take this equation and differentiate with respect to time and turn it around, we obtain this differential equation, which on the left-hand side gives us the positive fuel consumption rate R, which is the mass change per time, times the relative velocity, and it tells us that that change is equal to the initial mass of the rocket times the change in speed, dv on dt, which with our knowledge of kinematics we identify as the acceleration a. Substituting with r and a, we then obtain what's known as the first rocket equation. The burn rate of the fuel times relative velocity is equal to the rocket mass times its acceleration. So you can see that the acceleration of the rocket, and therefore the thrust force on the rocket, is a function of burn rate R and exhaust speed V relative. If we now take the earlier differential equation minus m dv equals plus dm relative velocity and integrate it on both sides, we obtain the second rocket equation, which is the difference between the final and initial velocity of a rocket is given by the product of the relative velocity between exhaust gases and the body of the rocket times the logarithm of the initial mass divided by the final mass. This second rocket equation tells us that increasing the mass ratio achieves the greatest speed. In other words, the more exhaust gases we can expel from the rocket body, the faster it will travel. Also, if we can reduce the initial mass by leaving dead mass behind, in this case by leaving dead mass on the moon, and staging the travel, we can increase the velocity. The two rocket equations with which the motion of any rocket can be explained are burn rate R times the exhaust gas speed is always equal to the inertial mass of the rocket, that includes the fuel that hasn't been burned yet, times its acceleration. That's known as the first rocket equation. The second rocket equation shows that the change of speed of the rocket is equal to the same exhaust gas speed, V relative, times the natural logarithm of the ratio of the initial mass, the mass that moves with the speed of VI, divided by the final mass, which is the mass that moves with the speed of Vf. This is known as the second rocket equation. We have just developed an understanding of the thrust force. We can write it down for every space vehicle by quoting the first rocket equation. However, we have not answered yet our second question. What is the gravitational force? In order to explain the gravitational force, we have to refer to Isaac Newton. Isaac Newton, who has been described as one of the most brilliant minds ever, in 1666, when he was 24 years old, developed the understanding of gravitation that holds today within classical physics. The story that led to this discovery and the development of the theory of gravitation by Newton is quite intriguing. In 1666, when Newton is 24, the university in Cambridge has to close due to the bubonic plague, which killed 15% of London's population. In order to escape, Newton retreated to his mother's place, where he grew up, in Woolthorpe in Lincolnshire. It is historically confirmed that it was there where the famous apple drop occurred and where Newton began to compare the forces on the apple and other objects on Earth with forces on the moon, which he might have seen in the sky above. Newton's intellectual achievement in doing this was remarkable. He considered apple and moon on the same footing. Thereby he did not distinguish between an earthly world and a heavenly world, which was the contemporary thinking. If Neil Armstrong's step onto the moon was a giant leap for mankind, then indeed Newton's intellectual achievement was such a giant leap as well, because it changed the prevailing ideas of antiquity that had remained in place until the 17th century. And Newton's thinking showed that there is only one physics for the entire cosmos. His reasoning indicated that humans and the Earth are just one part of a much wider world that is ruled by the same laws. Since this somewhat banal event of an apple dropping onto the ground had such immense consequences for humanity, leading us eventually to conquer the moon and landing there, let us read two quotes from contemporaries which confirm that this indeed happened. In the year 1666, Newton, retired again from Cambridge to his mother in Lincolnshire. Whilst he was pensively meandering in the garden, it came into his thought that the power of gravity, which brought an apple from a tree to the ground, was not limited to a certain distance from Earth, but that this power must extend much further than was usually thought. Why not as high as the moon, said he to himself, and if so, that must influence her, the moon's motion, and perhaps retain her in her orbit. Whereupon he fell a calculating what would be the effect of that supposition. The last sentence, written in the awkward English of the time, of course, means he immediately rushed to the house and worked out what he was thinking about. Another contemporary writes, when formally the notion of gravitation came into his mind, it was occasioned by the fall of an apple, as he said, in contemplative mood. Why should that apple always descend perpendicularly to the ground? Thought he to himself. Why should it not go sideways or upwards, but constantly to the earth's center? Assuredly the reason is, he answered, that the earth draws it. There must be drawing power in matter. And the sum of the drawing power in the matter of the earth must be in the earth's center, not in any side of the earth. Therefore does this apple fall perpendicularly or towards the center? If matter draws matter, this is really the crucial statement. Matter draws matter. That's a realization that the force between objects is due to the matter comprised by them. If matter thus draws matter, it must be proportion of its quantity. So the force, the gravitational force, is proportional to the mass in an object. Therefore, the apple draws the earth as well as the earth draws the apple. So it's a symmetric force, as required by Newton's third law, action equals reaction. Let us look at Isaac Newton's breakthroughs in detail, as they have led to the discovery of the universal law of gravitation. Firstly, before, Newton had already postulated his second law, namely that any force is always the product of inertial mass times its acceleration. This is true in general for any type of force. The big question is always, in any type of mechanics problem, what provides this force F that causes an inertial mass to accelerate with an acceleration A? So in this case, what provides the force that accelerates the apple downward and also accelerates the moon downward, and therefore provides a centripetal force that keeps it on its orbit? And impressed by his comparison of apple and moon, Newton answers, there must be a drawing power in matter, and this drawing power we now call gravitation. So Newton's first very important realization is that mass has not just one, but two properties. Mass can be inertial, but mass can also be gravitational. Inertial mass means the resistance of an object in reacting to an external force. Gravitational mass means the capability of an object to attract other objects. The unit, the dimension of both the inertial mass and the gravitational mass, is m, and measured in kilogram. However, Newton's first realization is that this equivalence nevertheless does not mean that the two are the same. Inertial mass is fundamentally different from gravitational mass. Newton's second important realization was that the apple falls to the ground. However, the ground also falls to the apple. And this is just paraphrasing Newton's third law, that action requires reaction. Just imagine lying on the ground and imagining that you're falling towards the moon. It's quite a thought. So gravitation is mass symmetric. The gravitational force on the inertial mass of the apple is due to the gravitational mass of the moon, and the force on the inertial mass of the moon is due to the gravitational mass of the apple. As we said before, inertial and gravitational mass are not the same, they are equivalent, and depending on perspective, a mass can be either inertial or gravitational. The important realization, the second important realization, is that gravitation is mass symmetric. Newton's third important realization explains why we still call the law of gravitation universal, the universal law of gravitation. This goes somewhat beyond physics itself. It has to be seen within the social context of the time. Contemporaries of Newton considered the earth, the place where humans are, and the heavens, a different place, where God and religion has its place. The suggestion, therefore, that the heavens as represented by the moon and earth as represented by the garden and Woolthorpe are ruled by the same laws at the time was considered by some as a statement of heresy. However, by insisting and underpinning it with evidence, Newton moved human self-understanding beyond Aristotle and made physics universal. Newton's fourth important realization takes us back to physics and the mathematical explanation of gravitation, namely that the gravitational force has a 1 over r squared dependence. And Newton underpinned this suggestion with quantitative support as provided by his moon calculation. It was well known at the time that the moon had a period of 27 days and that it was orbiting the Earth with an average orbital radius of about 60 times the Earth radius. Also, using the pendulum experiment, the gravitational acceleration, the little g on Earth, was known. Since the moon orbits almost on a circle and having a knowledge of rotational mechanics, it was then possible to express the force on the moon as a centripetal force. This slide summarizes Newton's moon calculation. This is the Earth attracting the moon and thereby providing via its gravity a centripetal force on the moon. Now, if one considers just 1 kilogram of the mass of the moon, the gravitation on the moon should be proportional to 1 kilogram times the gravitational acceleration at the distance r. That's not the little g on Earth, but that's the little g at the position of the moon. And that force, because the moon stays on its orbit, has to be equal to the centripetal force, which is mass times angular velocity squared times radius. So therefore, the g at the moon has to be equal to omega squared times r, assuming that the inertial mass and the gravitational mass are the same in magnitude. And that's in fact the suggestion that we just discussed a moment ago, the very important realization by Newton that gravitational mass and inertial mass are the same. This is where it goes into the calculation. Okay, g at the moon, gravitational acceleration at the moon, is omega squared times r. If we now substitute what we know about omega squared and about r, we obtain this term. We know it's 27 days, we work out how much that is in terms of seconds, we square it, and then we know the radius of the Earth times 60 gives us 3.84 times 10 to the 8 meters, and using the calculator we get 0.002724 meters per second squared for the gravitational acceleration by Earth on the moon at the position of the moon. If we now compare this g at the position of the moon with the g that we know on Earth from the pendulum experiment, which is 9.8 meters per second squared, we obtain a ratio between the two that is 9.8 divided by 0.002724 meters per second squared, and that is equal to 3,598. If we take the square root of this number, the square root of 3,598, the square root of this ratio here, we obtain a neat 60. That means we have found that our result is consistent with the radius of the moon orbit, which is 60 times the Earth radius. This demonstrates that the gravitational acceleration has to decrease with distance as 1 over distance squared. And if this applies to the gravitational acceleration, this is also true for the gravitational force. So as distance increases, the gravitational attraction decreases with 1 over distance squared. Mathematically, Newton's realizations can be summarized in this universal law of gravitation. this law, we have the gravitational constant g, not to be confused with little g or little g at the moon. This is a universal natural constant that Newton in fact did not know because it hadn't been measured at the time. So this is the universal gravitational constant. Then we have two masses, one acting in its inertial capacity, that's the mass on which the gravitational force acts, and then another mass, m2, which acts in its gravitational capacity, that's the mass that creates the force on mass m1. Furthermore, do we have the 1 on r squared dependence that Newton underpinned with his moon calculation, and which we now know is correct. And finally, we have a unit vector which indicates the direction. So if we have a mass m1 and a mass m2, the force is always acting along the line connecting the two masses. So m1 pulls m2 towards m1, and m2 pulls m1 towards m2. Newton didn't know the universal gravitational constant capital G, but first Cavendish and then others with setups like this, or that, demonstrated that it can be measured and obtained values for it. In order to obtain utmost precision, the Cavendish type torsion balances are set up to have a symmetric arrangement with two larger masses attracting two smaller masses. The attraction causes a torsion of the central wire, at which there is a little mirror attached, and these days, with a laser being reflected at that mirror, the torsion of the wire can be measured. Considering the geometry and the torques acting on the smaller masses, the constant G can be determined. This is a schematic illustration of the Cavendish experiment. The gravitational attraction between the large and the small masses induce a torque on the torsion wire, which is projected via this laser beam onto a scale. This video shows an actual experiment to measure the universal gravitational constant G using the Cavendish apparatus. You can see the original laser position is here. The masses have just been changed in position, and that induces an oscillation on the torsion wire, which is projected onto the wall as an oscillation of the laser spot. And it takes some time. Time is given here in minutes, 24 minutes, and typically one has to wait about an hour for the torsion wire to settle so that the new rest position of the laser beam becomes apparent. In this graph, the damped oscillation is also indicated, and you can see we're now coming to a situation where we can identify this black line as the new rest position. So the laser beam has shifted from up here to down there due to the gravitational attraction between the large masses and the small masses. The accepted value today of the gravitational constant G is 6.674 times 10 to the minus 11 cubic meters on kilogram on second squared. It should be noted that it is the least well-known physics constant and that it has to be measured in a laboratory rather than with astronomy, and the experimental challenges in the laboratory cause the large uncertainty in the measurement. The Universal Law of Gravitation, published first by Newton in 1687, states that the force by an attractor M on an inertial mass m is given by the gravitational constant G times inertial mass times the mass of the attractor divided by the distance squared, the inverse square law. The force is a vector quantity and its direction is always along the line between the inertial mass and the attractor mass, pulling the inertial mass towards the attractor. It is an attractive force. The gravitational constant G has been measured to be equal to 6.674 times 10 to the minus 11 Newton times meters squared on kilograms squared in the SI system. The gravitational force is one of 4 fundamental forces. And Newton's great achievement includes that he identified, by stating the universal law of gravitation, that the entire cosmos has a common physics and that there is no separation between Earth and the heavens. We started off by pondering about the forces involved in the landing of the Lunar Module of Apollo 11 on the Moon in 1969 and decided it was the thrust of the landing module and that it had to be at least as large as gravitation. I've shown you that the thrust force is a result of the rocket equation, and we just understood that gravitation is a consequence of Newton's universal law of gravitation. We are now in a position to compare the two forces and decide if the lunar module is indeed in a position to land on the Moon. The thrust force is 44,400 newtons. And applying the universal law of gravitation, we can substitute with the universal gravitation constant the mass of 15,000 kilograms for the lunar module times the mass of the Moon, which is 7 times 10 to the 22 kilograms, divided by the radius of the Moon, which is 1,700 kilometers squared. If we plug this into the calculator, we find that the gravitational force during landing onto the lunar module is 24,000 newtons. And you can see that the design of the module, giving it a thrust of 44,400 newton, is sufficient to overcome this gravitational attraction, and the module will not crash land. Having arrived on the Moon, we might ask ourselves the question what the gravitational acceleration is. We know that the gravitational acceleration on Earth is equal to 9.8 meters per second squared. What is it on the Moon? We can work it out using the universal law of gravitation. The force F on a mass, which might be the inertial mass of our body, the inertial mass of a person or some other object, as an apple, like an apple for example, or a car, whatever, is equal to this mass, this inertial mass, times the gravitational acceleration. And if we're on the Moon, on the surface of the Moon, it's the gravitational acceleration on the surface of the Moon, g Moon. And that force is provided by the gravitational attraction of the Moon, which is equal to g times the same inertial mass m times the mass capital M of the attractor of the Moon divided by the distance from the center square. So here we have the gravitational mass as opposed to inertial mass, the gravitational mass of the Moon divided by the distance square from the center of the attractor, the center of the Moon. The distance from the center of the attracting object, which in our case is the Moon radius. Now, if we look at this and divide, we see that the inertial mass is on both sides. If we divide by the inertial mass, then we obtain an equation for G Moon, and G Moon becomes gravitational constant times attractor mass times distance squared from the center. Substituting for the Moon means that we have to use the universal constant of gravitation, 6.674 times 10 to the minus 11 Newton meter squared on kilogram squared, times the mass of the Moon, which is 7 times 10 to the 22 kilograms, divided by the radius of the Moon. We are at the surface, 1,700 kilometers squared, and if we plug that into the calculator, we obtain that that's equal to 1.6 meter per second squared. So if we compare the gravitational acceleration on the Moon with that on Earth, we find that this is about 1/6 of the gravitational attraction on Earth. That's why the astronauts bounce about. If we do the same calculation for mass and work out G mass, we again substitute with the universal gravitational constant. It is universal, therefore it does not change. Then we multiply with the mass of mass, which is about 10 times that of Moon, so it's 6.4 times 10 to the 23 kilograms, and divided by the radius of mass. So that increases, so this is an interesting point. This increase in mass increases the acceleration, but because mass is also larger, it has a larger radius of 3,390 kilometers squared. That reduces the gravitational acceleration, so that in total, if we plug this in again into the calculator, we obtain 3.7 meters per second squared for mass. And again, if we compare with Earth, we find that's about 1/3 of the gravitation of Earth. We've just seen that G, the gravitational acceleration, depends on the distance r from the attractor with the mass m. And the equation for this is G vectorial is equal to minus G m divided, this is the attractor mass, divided by the distance square from this attractor, from the center of the attractor. And it's a vector, so we define the direction as an r unit vector that points away from the attractor, and therefore we need a minus sign to indicate that it is attractor. So test mass, a mass little m, which might be located here, is accelerated with an acceleration g towards the attractor with capital mass m and the center. So we have our point of interest where the mass is located at a distance r. However, the gravitational attraction is in the other direction. This is our little g, indicating the acceleration of the mass little m, and therefore we need a minus sign in that equation. The equation tells us that if we move our mass further out to infinity, then this r becomes infinity, and therefore g at infinity, due to this attracting mass capital M, tends to go to 0. We can also see that little g is defined for every point in space, for every r. It's symmetric about this center of the attractor M, and it can be defined for every distance r, and therefore for every point in space. So g is defined for every point in space, which allows us to introduce the concept of gravitational field. A field is a field of vectors. So when we talk about field in physics, we mean a vector, a mathematical vector field. And in this particular case, the vector field represents the gravitational acceleration g. It's sensible to introduce a gravitational field because the situation has an analogy to electrostatics. In electrostatics, the force is the Coulomb force, and the electric field associated with that, as you'll find out later, is equal to either plus or minus, depending if you've got two equal charges, then you have a plus sign, or if you have anti-equal charges, you have a minus sign here. And similar to what we have here, starting with a constant, we start with a constant in electrostatics, which in that case is not a single variable, but it's called 1 over 4 pi epsilon, but it can be considered just one constant, times q, capital Q, which takes the place of the attractor mass. So this is the attracting charge, if you like. If we make this negative and we have a positive test charge, then this positive test charge attracts the negative. This positive attracting charge attracts the negative test charge, and we have an inverse square dependency with distance. And again, the situation is symmetric with respect to the attracting charge. So we get the r unit vector. You can see this equation looks very similar if we compare it with the gravitational field. Yeah, the electric field strength takes the place of a gravitational field strength. There is a difference here. A gravitational field can only be attracting. The vectors always point towards the attractor. In electrostatics, they can also point the other way. Therefore, we have plus or minus sign depending on the sign of the test charge. But we also have a constant, different constant, because it's electrostatics. We have the 1 over r squared dependence, and we have an attracting or repelling charge as opposed to an attracting mass in gravitation. A further reason to talk about gravitational field is that it anticipates Einstein's theory of gravitation, which is also a field theory. In general, field theories are very important in physics, and it's good to become familiar with them. Now, if we define the gravitational field vector everywhere in space, then we can visualize it like this. We have our attractor of mass m, and if we take a point here, we can draw a field vector that points inward. We have a similar situation here. The magnitude doesn't change, but the direction changes. If we go further out, the field vectors become shorter because the field strength weakens, and we obtain a picture like this. And here we talk about field vectors indicating the strength of the gravitational field, but one can also illustrate the same situation using field lines. They then look like this. Field lines indicate the direction of the field, and somewhat qualitatively, the more denser they are, here the field lines are really dense, the stronger the field is. Whereas in the case of field vectors, the length of the field vector indicates the strength of the field. In both cases, the direction, the line, indicates the direction of the gravitational field. So this is called field lines. And if we've got a spherical attractor, then the field lines have spherical symmetry. However, one can also have other situations, for example, in good approximation at the surface of an attractor, for example, near the surface of the Moon, or for that matter, near the surface of Earth. The field lines are effectively parallel to each other, and they look like this. And if you draw that in terms of field vectors, you have to have at this point a relatively large field vector. But if you go further away from the Moon surface, the magnitude of gravitation becomes less, so therefore the vectors become shorter, and if we go even further out, they become even shorter. While Neil Armstrong and Buzz Aldrin visit the Moon, Michael Collins stays behind in the command module and orbits the Moon. The command module is kept on its orbit by the Moon's gravitational force. What effect has Earth's gravitation on the command module? During the Moon landings, the command module stayed on an orbit about the Moon. Let's sketch it. This is the Moon with the gravitational mass m, and at a rather close orbit at a height of only about 100 kilometers, we have the command module orbiting the Moon. And this is possible because the Moon attracts the command module with the gravitational force Fg that provides the centripetal acceleration to keep the module with Michael Collins, the pilot Michael Collins, on orbit. So the command module stays on a circular orbit, and in principle at uniform motion at constant tangential speed. And that's possible because the centripetal force mv squared on r, whereby r is this distance, so it's the height, r is equal to the height plus the radius of the Moon, which is 1.7 times 10 to the 3 meters, and this height is 100 kilometers, which is, no, this is kilometers. This is kilometers, and this is just 100 kilometers. So altogether we have 1.8 times 10 to the 6 meters for r. So that centripetal force is provided by the gravitational attraction of the Moon, which according to the universal law is g times the inertial mass of the module, which is, you can look this up, 10 tons, so it's 10 to the 4 kilograms about, times the gravitational mass of the Moon, which is 7 times 10 to the 22 kilograms, divided by the same radius here, squared. If we now look at this equation, we can see that we have m on both sides, the little m is on both sides, it cancels, and we can rearrange to obtain for a given radius that we need a certain tangential speed v, which is given by the square root of gm divided by this radius. That's the wrong one. No, not just d divided by this radius r. I've forgotten to tell you that the square here cancels with the radius there. So this is the same r. This r shows up here, and we find that if we fix the radius, we need a certain speed to stay there, or the other way around, if the tangential speed of the command module is fixed, then it can only park on a certain radius about the Moon. Using the actual parameters, an altitude of 100 kilometers, we can substitute, and we find that we need to calculate the square root of capital G, 6.674 times 10 to the minus 11 Newton meter squared on kilogram squared times the Moon mass of 7 times 10 to the 22 kilograms, and divided by this r, which is 1.8 times 10 to the 6 meters. And we find that this altitude, this parking orbit, this particular parking orbit that was used, requires a tangential speed of 1,611 meters per second. Now, the Moon is not the only gravitational attractor on the command module. On the photo earlier you saw the Earth in the background, and although at a much larger distance, it also has a gravitational pull in principle on the command module, because gravitation has an infinite range. Gravity has infinite range. That's a very important property of gravity, and that means the Sun, which is not at infinity but far away but not at infinity, also should have a pull, and for that matter any other massive body in the sky. But let's just look at Moon, Earth and Sun and see how they affect the motion of the surface module. Let's draw the Moon once more, and the circular orbit. I'm exaggerating here. It's much closer, of course, as we just discussed. This is it. Now we have a pull, gravitational pull by the Moon, but we might also have Earth here, which causes a gravitational pull in this direction, and at some further distance the very large Sun that will pull in this direction. How do we deal with this situation? Well, we need to apply what's called the principle of linear superposition. Gravitational forces are mutual between two attracting bodies. However, if there are several of those reacting pairs, then we need to consider the vector sum, and that's stated in the principle of linear superposition. It says that the net force, the net gravitational force on an object is the vector sum. That's important. We not only need to consider magnitude but also the direction of all those forces. The net force is the vector sum of all gravitational forces. And that's in principle an infinite number, because there's an infinite number of attractors in the universe. However, within reason, one should only consider the ones that are significant. So in this case, we might have three that are significant: the Moon, the Earth, and the Sun. And I've drawn you a diagram here. Of course, the situation changes if the module goes to the other side. Then suddenly the pull from the Earth is in this direction, and the Sun now pulls in this direction, and the Moon pulls in that direction. Let's consider the first situation. I'm drawing a magnified free body diagram here. So this is the effect due to Earth. The effect due to Moon should be much larger, and Sun may be like this. So what is the net force on the surface module? We have to consider all these contributions. So let's first look at the combined effect of Earth and Sun, which is this resultant vector here. And now we combine this resultant vector with the force of gravity due to the Moon. We have to draw another parallelogram, which is this, and we find that the resultant net force points in this direction. So this is the net force vector that affects the motion of the command module. And you can see, if I draw the vector in here once more, you can see it's not tangential to the motion. So that means we have, well, I should say it's not radial to the motion. In fact, it has a tangential component. So that means the effects of Earth and Sun, effects of Earth and Sun can cause an acceleration or a deceleration of the module, and this may have to be corrected using the thrusters of the module, for example, if these effects are significant. In order to find out if Earth and Sun have a significant gravitational pull on the command module, let's work out the magnitudes that come into play. And again, we do that using the Universal Law of Gravitation. For the Moon, the maximum gravitational force in that distance, F, is given by constant g times the mass, the inertial mass of the module, times the gravitational mass of the Moon divided by r squared. So we substitute here 6.7 times 10 to the minus 11 Newton meter squared divided by kilogram squared times 10 to the 4 kilogram. That's the inertial mass of the module, times 7 times 10 to 22 kilogram. That's the gravitational mass of the Moon. And the command module is at a distance of 1.8 times 10 to the 6 meters, which goes in squared. If we work this out, we find that the gravitational pull is 1.5 times 10 to the 4 newtons. Now, if we do the same calculation for Earth, we find that this first bit of the calculation, this bit stays the same, but here we need to replace with the Earth mass, which is 6 times 10 to the 24 kilograms, so 2 orders of magnitude larger. However, the radius is also larger, which is 4 times 10 to the 8 meters, which goes in squared. So we have an increase of gravitational pull of 2 orders of magnitude here, but the distance gives us a decrease of 4 orders of magnitude. So we would expect at least 2 orders of magnitude less for the Earth. And indeed we find that the force, the maximal gravitational pull due to Earth is 2.5 times 10 to the 1 Newton, which is significantly less than the one for the Moon. For the Sun, we again have the same factor here, but then we replace with the mass of the Sun, which is 2 times 10 to the 30 kilograms, and the distance from the Sun is 1 astronomical unit, which is 1.5 times 10 to the 11 meters, which goes in squared. So compared to the Moon, we have an increase of attraction, 22, 30, that's 8 orders of magnitude, and we get a decrease here because we have 5 squared, that's 10. So the net outcome is a gravitational pull that is 2 orders of magnitudes less. And indeed, if we plug in the numbers, we find the force due to the Sun is equal to 5.9 times 10 to the power of 1 newtons. And you can see that this is still very much less than what we obtained for the Moon. However, interestingly, the Sun has twice the effect on the command module than Earth, despite it being much larger, much further away. However, its mass is so much more significant. This is another example of the application of the principle of linear superposition to a situation where we have many masses, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 masses, and a high degree of symmetry. And we want to know the direction of the net gravitational force on the central particle. This central particle, which way will it be pulled? What is the net effect of all those gravitational pulls? Assuming that all these gravitational masses have the same magnitude. Let us solve the problem by considering the 1, 2, 3, 4 dashed lines. Starting with this horizontal line, we see that on the left we have a particle pulling the central particle to the left, and on the right we have an anti-equal force pulling to the right. So the net contribution of this pair is 0. The same is true for this combination of particles. Here we have a weaker pull because we're further away from the center, and we have an inverse square law. We have a weaker pull on the central particle, however it is compensated by a pull in the other direction of the same magnitude. The vertical dashed line is complex. Here we don't have symmetry, so let's first look at this dashed line here. And again we have a symmetric situation. These two particles both pull to about 2 o'clock, and here we have particles pulling at in the direction of 8 o'clock with the same magnitude. So again the net effect of this pull is 0. However, the one line we have left out, the vertical line, is different. Here we have a weak pull to the bottom, which is compensated by a pull of equal magnitude to the top. So this pull and that pull compensate each other. However, left is now one force that is also pulling upward due to the gravitational attraction of this particle here, and that is not compensated because here we don't have a particle. So the net force on the central particle is a relatively strong pull upward. After returning to the Eagle landing module, the two astronauts, Armstrong and Aldrin, had to overcome the gravitation of the Moon to return back to the command module. And they could do that by relaunching from Tranquility Base using the thrusters of the ascent stage of the landing module Eagle. And the speed they could achieve with the ascent stage is given by the second rocket equation, which we talked about earlier, which is the speed that can be achieved is equal to the constant relative velocity between exhaust gases and module. So one can say this is the constant exhaust speed times the logarithm of the mass ratio. Mass initial divided by mass final. So this is the mass of the ascent stage on the Moon, including the fuel. Mass initial, mass with fuel, and then MF is the mass just before docking again with the command module, the final mass. And if we plot this function, if we plot V as a function of the final mass, because the initial mass is constant, the final mass is variable because the more fuel is exhausted, the less the final mass becomes. We obtain this logarithmic function, logarithm of m initial divided by m final. So by determining the amount of exhaust fuel they were going to use, the astronauts could determine their final speed. But the question of course, what speed is required? What velocity, or in this case speed, v, is required to escape a gravitational attractor? Which in this case is the Moon. And this speed, because it's important for space travel, has got the technical term escape velocity. So what is the escape velocity? What is the minimum velocity required to escape the Moon in the ascent stage of the landing module? It is defined as the speed required to reach infinity without being pulled back by the gravitational attractive of a mass. Pictorially, we can sketch it like this. We have the Moon, or more generally the attractor, and we have a smaller mass, in this case the ascent stage of the landing module, which tries to escape all the way to infinity. And in order to achieve that, the mass little m requires an escape speed. What escape speed does it require? This can be worked out using the principle of energy conservation. We write the total energy, E total, has to always be equal to the sum of the kinetic energy K plus the potential energy U, and because of energy conservation this is constant. Let us apply this to a spacecraft. In this case, if we escape a gravitational attractor at infinity, or at a distance that tends to infinity, r equals infinity, we need no more kinetic energy to escape. Therefore, we can write in infinity the kinetic energy is zero. We have already escaped, no more energy is required. The potential energy in infinity will have a certain value. And you remember that in regard to potential energy we can always define it with respect to a constant value. So it is clever to choose infinity as reference point for the potential energy scale, and to define that at infinity the potential energy, the gravitational potential energy, should be zero by definition. We then obtain something that looks maybe initially trivial or simplistic or pointless, namely that the sum of kinetic energy and potential energy in infinity is 0 plus 0 equal to 0. Well, let's see where we get with this. We require that the total energy is conserved, so we can therefore consider now the situation at the surface of the attractor. Let me sketch the situation. So this is our capital mass M, the attractor with a defined radius r, and we're now not in infinity anymore, but right on that surface. Then in this situation, the total energy, now not in infinity, you notice this is changed. We have now the total energy at r has to be equal to the total energy at infinity, because of we can write energy conservation. And we know that in infinity it's 0. However, that 0 is now created in a different way, by a different ratio of kinetic to potential energy. We might have, well, it cannot be a ratio, by a different sum of kinetic and potential energy, I should say. And you can immediately conclude that one of the two has to be positive and the other one has to be negative to achieve a 0. We also know from our knowledge of mechanics that the kinetic energy is always equal to this little m times v squared, whereby v would be the speed of the mass at that point divided by 2. But what we don't know at this point is what is the potential energy, what is the gravitational potential energy. U of r. What is this? This is again our attractor, and this is our mass little m in infinity, and the potential energy arises if we move this little mass m from infinity to the surface. So that means U of r is equal to the work associated with moving little m from infinity to r. So we write it's the work associated with the path from infinity to r. Work is defined as positive if external effort is required to move a mass over a distance. However, here the situation is different. Internally, the attraction of the large mass will pull the small mass into its vicinity. So therefore we would expect that the work is negative and the potential should be negative. Let's see if that's really the case. So we write down that our work is the integral from infinity to r over the force applied onto our little mass times the path differential dr prime, which is also a vector. Now we notice that our integral goes from a large number to a small number, so we have to swap the limits and therefore obtain this minus sign, swapping integration limits. And we now have r to infinity and we have F scalar product dr prime. Let's look up where these vectors are. The attractive force vector points towards the attractor, and we're also traveling from infinity towards the attractor. So both vectors, F and dr prime, point in the same direction to the left. So we can remove the vectors from our integral and write that this integral is equal to minus integral from r to infinity scalar product of F times dr prime. Now we know what F is. F is the gravitational attraction due to capital M, and that is represented by the Universal Law of Gravitation. So we can apply the Universal Law and substitute, and we find that we get minus capital G M, the masses can be moved out of the integral, times the integral r to infinity of dr prime divided by r prime squared, which is the inverse square dependence of the universal law. You've seen integrals like this before, possibly. If we now carry out the integration, we find that this is equal to minus g m, and the integral of 1 over r squared is equal to minus 1 over r. So this is minus 1 over r prime, and we get, with the limits are r to infinity, we can substitute with these limits, and we find this is equal to minus g m times 1 over infinity gives us a 0, and 1 over r is 1 over r, so we have minus 1 over r. These two minus signs cancel, but we're left with the 1 at the front. So indeed, we have shown that the potential, which is equal to, this is how we started off, this is equal to the work going from infinity to r, and that's equal to the potential at the position r. That potential at position r is, as expected, negative, and it's equal to minus g m divided by r. You can see that for every point in space we have a defined potential, which is given by the negative gravitational constant times the product of masses divided by r. This is known as the gravitational potential energy. And now we are in a position to answer our question: what escape velocity do we need to leave the moon, or any planet, or any attractor for that matter? Let us locate ourselves again onto the surface of an attractor capital M, and rewrite again the equation of energy conservation, which is E total, which we found is equal to 0 if we define the potential energy 0 in infinity, and is always made up out of kinetic plus potential energy. So at the surface we have the kinetic energy plus what we just worked out, the potential energy, which is minus gmm divided by r, and the kinetic energy is equal to mv squared, whereby the v is the escape speed divided by 2, because that speed will get us into infinity without violating energy conservation, and reaching infinity exactly with an kinetic energy of 0. So that's why v is the escape speed. If we then rearrange this equation, we find that v is equal to the square root of 2gm divided by r, and this is known as the escape velocity. You can see that the two m's cancel, we are left with the r, and the v squared disappears because we're taking the square root, and this 2 ends up here. The g is already there. So this is how we can derive the escape velocity. It is a consequence of energy conservation and results from the fact that in infinity we don't need any kinetic energy anymore. We have already escaped, and therefore the kinetic energy that gives us a zero energy balance for any point in space is equal to the escape velocity. The equation we have just derived is important, so that we should take note of it. It defines the escape velocity, or better, escape speed, because it is a scalar and not a vector. The escape speed is the launching speed that allows a space vehicle to reach infinity just, which means at zero speed in infinity. And it is equal to the square root of 2 times the gravitational constant times the mass capital M, the mass of the attractor, divided by the launching distance r. We notice that the escape speed is independent of little m. It is therefore independent of the mass of the rocket or the mass of the space vehicle. It is a universal speed, which only depends on the mass of the attractor. For the Moon, we can calculate that the escape speed is 2.4 kilometers per second, which is significantly less than the escape speed for Earth, which is 11.2 kilometers per second, due to its larger gravitational pull.
Okay, I'm going to get the probe. 99, proceeded, 3, 2, 1, ignition. Burn away, Houston. Vector good. Ag thought. It's over. I hear you have good thrust. Houston, we're in the blind and we're go. Right here, we'd like the Ags to auto. Okay, I got good luck. No. Trying to hold. Okay, Houston, coming up on 2 minutes. Challenger, Houston, you're go at 2 minutes. We'd like Ags to move control auto. Over.
You might wonder how the total energy can stay zero if kinetic energy clearly changes so dramatically. This becomes apparent if we look at the situation in a diagram. So the energy conservation, as we discussed, requires that the total energy is zero and that this is always made up out of kinetic and potential energy. If we draw the situation whereby we have the distance from the attractor r on the x-axis, and we have the total energy in this diagram in blue, then for all distances that should stay zero. And that is indeed possible if in green we have the kinetic energy go down like this with 1 over r, and the potential energy also decrease, but starting at a negative value. So we're going from negative to 0, and here we're going from positive to 0, whereby at every point of distance from the attractor, the magnitude of the gravitational potential energy is equal to the magnitude of the kinetic energy. The gravitational potential energy is a very important concept in planetary motion. It is defined as U of r equal to minus g times little m capital M divided by r, whereby the little m represents the inertial mass, the capital M represents the gravitational mass of an attractor, and the potential energy is negative because the gravitational force performs work, if you like, for us. We don't have to perform work to move the mass towards the attractor. The attractor pulls the mass in. So that's why the potential energy is negative. The gravitational potential energy is defined for every point in space, and importantly, it can be successfully used to solve many problems, in particular then when it's defined as zero at infinity. Then, using energy conservation, it balances the kinetic energy and the two add up to a total energy of zero. Our understanding of gravitational potential energy raises the question if this understanding is indeed consistent with the familiar equation U equals mgh. Let's try and work this out. This is our apple on the ground. That means it is at the distance of r from the center of Earth, and we're lifting this apple to a height of h. Then the gravitational potential energy is given as u at the position r plus h, u of r plus h, and it's equal to minus, remember it's negative, times gravitational constant times the product of the mass of the apple, that's the little m, and capital M is the mass of the Earth, attracting the apple downward, and the new distance is r plus h. So the change in potential energy in going from the ground to the height h, the delta U, is then given as the difference between this new potential energy and the original potential energy U of r. If we substitute, we put this in here, minus, there's another minus sign because the definition is negative. Now at the ground we have minus g capital M divided by r. Doing some algebra, we find that we can pull out g m and the minus sign, and we obtain 1 over r plus h minus 1 over r. We bring this term onto a common denominator and obtain minus h divided by r times r plus h. This can be simplified further. In particular, we can pull out the r from here to there, so that we get rid of the minus sign and now have plus g mm divided by r and a term in bracket. We multiply with r on r and pull out another r, and now in front we obtain g times mm divided by r squared. And that is of course the gravitational force at the surface of the Earth, which we know as m little g, m times little g. So we replace the factor in front with m times little g and now have a term in the bracket hr divided by r plus h. What is that equal to? Well, remember that the distance to the center of the Earth is rather large. We're talking about 6,000 kilometers. And typically lifting the apple, it might be 1 meter, 10 meter, 100 meter even, is small compared to 6,000 kilometers. So therefore, this term here is, in good approximation, equal to 1. So therefore we now have shown that the change in potential energy, lifting the apple from the ground to a height h, is equal to the familiar m times g times little h. Before the astronauts could relaunch from the moon with a speed in excess of the escape speed, they had to work out what would be the right timing. How would they arrange a rendezvous with the command module with Michael Collins inside that had been orbiting about the moon while they were on the surface? At what time will the command module be over the landing site? That was the question that they had to answer, and they could have done that using Kepler's laws. This is the situation once more. The moon at some distance from its center. I'm exaggerating that distance. In fact, it was only 100 kilometers, and the radius of the moon is 1,700 kilometers. But at that distance, we have the command module orbiting, and we looked at this situation before. So let's write Apollo 11 command module orbiting with a period t. And that period t we need to know in order to decide when we're here at the landing site when we need to launch to get there in time. We don't want to launch when the command module is on the other side, because then we run out of fuel. So we want to know when the command module is here so that we can rendezvous and dock. And in order to do that, we need to know the period of revolution for the command module. We can work this out if we express the centripetal force, which is provided by the universal force of gravitation. Universal gravitation force. So that we obtain G mm, as before. We've done this step just a while ago before, mv squared on r. We did this in order to conclude that the command module has to be on a certain radius for a certain speed. But now we're interested in the period for a given radius. We can rearrange that equation and simplify it to obtain G capital M on R is equal to V squared. You can see we have divided by the the inertial masses on either side, and we've taken out one of the R's, and we get this. You're familiar with rotational motion, and you can replace the V squared with omega squared, and you do that using the equation V equals omega times R. Formally factorial V equals omega cross R, but here everything is at right angle, so we can write V equals omega times R. So we obtain on the right hand side omega squared R squared. You probably also remember the relationship between omega and period, which is omega is equal to 2 pi, the displacement, angular displacement, divided by period t. Let's substitute with that, and we obtain on the right hand side 4 pi squared divided by t squared times r squared. So we've got the period, that's what we were after, but we've got r on both sides, so therefore we move this r squared to the other side, and we obtain gm divided by r to the power of 3 is equal to 4 pi squared divided by t squared, and this is in fact Kepler's third law for circular orbits, Kepler 3. Normally it's written like this: t squared divided by r cubed is equal to constant. And that's possible because you can see that g is constant, and for a given attractor like the moon in this case, or if we talk about the motion of Earth about the sun is the attractor, this would be the solar mass. So the mass is constant for a given attractor, g is universally constant, and 4 pi squared of course is constant. So we can write for any planetary motion, orbital motion about an attractor, we have t squared divided by r squared is constant. And if we consider another orbiter, let's say a piece of space debris which happened to be about the moon, then that will orbit the moon with a different period, and we can, so we have T1 R1 for the command module, and for the space debris we might have T2 squared divided by R2 cubed is equal to the same constant, and combining this equation with the original one for the command module, we then can also write that for two orbiting masses about an attractor, it is always true that the ratio of the period squared divided by the radius cubed has to be the same. So it's now T2 squared divided by R2 squared, and this is known as Kepler's third law of periods. From this you can see there are two more which we talk about in a moment, and in order to distinguish them they have these additional identification, and this one is known as the law of periods because it contains, in this case if we write it this way, two periods, T1 and T2. So Kepler's third law of periods refers to a given attractor and may be written as T1 squared divided by R1 cubed is equal to T2 squared divided by R2 squared, whereby T are the periods, that's why it's referred to as the law of periods, and R1 and R2 are the radii with respect to the center of the attractor of the orbiting masses. And in words we can say, and that's how Kepler originally formulated it, the ratio of the squares of the periods of two planets. From this you can see this doesn't just apply to space vehicles but also to planetary motion about the Sun or about some other star, is the same as the ratio of the cubes of their radii. And now there are two things we need to remark here. Firstly, this law of periods was stated before the universal law of gravitation. It was discovered empirically by observing the planets before, about almost 100 years before Newton's law of universal gravity. However, as you've just seen, it is not a natural law, it is simply a consequence of the universal law of gravitation. So the fundamental law is the universal law of gravitation, and Kepler's third law, and for that matter the other two laws as well, derive from the universal law of gravitation. So Kepler's laws are derivations from Newton's universal law of gravitation. Now, as part of this presentation, I don't want to demonstrate that in detail, but Kepler in fact originally wrote not radii, but he talked about semi-major axes. Why is that? And that's because the situation can be generalized to elliptic motion. And you will find that in fact most planets don't follow a circular motion but an elliptic motion, and in order to geometrically define an ellipse you have a focal point and you have a minor axis, which is the vertical one, and a major axis, and the important parametrization in this context is the semi-major axis, which is the distance from here to there, and it's usually referred to as little a. And within this generalization one can express Kepler's third law as the ratio of the squares of the periods of two planets is the same as the ratio of the cubes of their semi-major axes. And mathematically that means that the radii here are replaced by the semi-major axes A1 cubed and A2 cubed. This is a simulation of our solar system. You can see that all the planets are effectively in one plane. We're now zooming in, and importantly you realize that according to Kepler 3, the inner planets like Mercury here go much faster with shorter periods than the outer planets like Mars or Jupiter or Saturn or Pluto. Here you can see Mars is going much more slowly than Mercury or Venus. Now we can help the astronauts using Kepler 3. We can work out that the period for the command module is given by the square root of this term. We substitute appropriately universal constant, mass of the moon, and the distance, which is the moon radius, plus 100 kilometer altitude, which gives us 1800 kilometers, which goes in cubed. We work out the square root and we find that that period is about 1.9 hours. So Michael Collins in his command module orbits the moon with a period of 1.9 hours, and with the knowledge of that it's then possible to launch the Lunar Module ascent stage at the right time so that it can rendezvous with the command module. Johannes Kepler lived from 1571 until 1630. He was an assistant of Tycho Brahe in Prague, and he analyzed data recorded by Brahe. This allowed him to study and improve the Copernican theory of planetary motion, and his work laid the foundations for Newton's later discoveries. What are the first two laws by Kepler? So let's write in the limit of circular orbits. We have the central with a mass of m, and we have an inertial mass, for example the command module, orbiting about it. Then the force that acts is always perpendicular on the inertial mass m, the gravitational force g. There are no other forces, and more specifically there are no other external forces. And from the mechanics of rotational motion you know that that means that angular momentum is conserved, and that means the motion is circular in a defined plane. And that's in fact the statement of Kepler 1, that planets move in circular orbits with the attractor in their center. Kepler's first law, which you see also follows directly from the Universal Law of Gravitation and the physics of rotational motion, expressed in the limit of circular orbits. This area A, and this is the topic of Kepler's second law, the area A. How does that area A change with time? So we're interested in the change of dA with respect to time. If we draw that area a little bit larger, we get maybe something that approximates a triangle. Yeah, I'm neglecting the curvature here, which is sensible in the limit of differential areas. And then we can look at this area as a triangle, and every triangle has an area which is equal to 1/2 the height times its base. So in this case, the height is equal to r, the radius vector, the length r, and the base is in good approximation r times d theta, whereby theta or d theta, the change in angle, is that angle here. So the height is r, the base is r times d theta, and trigonometry tells us that the area A is equal to 1/2 height times base. So therefore, in the differential limit, the change of the area with time is equal to 1/2 r squared. We've got two r's, this one and that one, r squared times the time change of the displacement angle. And we know from the mechanics of rotational motion that that is equal to rotational speed omega, so we can therefore write 1/2 r squared omega, and that is constant, because omega is constant for uniform circular motion, and certainly for a circle the radius is constant. So that means, briefly, dA with respect to dt is constant, and that is Kepler's second law, expressed here in the limit of circular orbits, and is referred to as the law of areas because it contains the area A, whereas the first law is referred to as the law of orbits because it discusses the orbit of a planet about an attractive mass. As already pointed out in connection with Kepler's third law, the first and the second law can also be generalized to include elliptical orbits. Planets move in elliptical orbits. And you know, of course, that a circle is a special elliptical orbit. So the circular motion is a special case of Kepler's laws. Planets move in elliptical orbits with the attractor, that's the mass m, capital M, at one focus. That is the first law. And you can see that the only thing we've changed here with respect to circular motion is that we've replaced the center with the statement at one focus of the ellipse. So if this is an ellipse, the mass m is at the focus. If we consider the special case of a circle, then focus and the center of the circle fall into the same place. And Kepler 2 reads a line that connects a planet to an attractor of mass capital M sweeps out an equal area A in the plane of the planet's orbit over equal periods of time. You have seen in this presentation that the development by Newton of the Universal Law of Gravitation represented a giant leap forward in the development of human thinking, which not only has influenced many aspects of the development of humanity over the last 300 years, but not the least allowed us to conquer the moon.
Columbia fired out of lunar orbit to begin its 3-day fall back to Earth, where the recovery fleet was waiting for its splashdown in the Pacific.